Right, here we get to the beginning of chapter 4. You'll start off in section 1.1, which is about maximum and minimum values, which we also use the word in calculus, extrema. So let C be a number in the domain D of a function f. Then f of C is defined as the absolute minimum of f on D if f of C is greater than or equal to f of x for all values of x in the domain of f, and the absolute maximum of f on D if f of C is less than or equal to f of x for all x an element of the domain of f. So let's take a look at some functions and some examples here. So let's graph each function in the given domain and determine the absolute maximum or minimum points. If I were to graph x squared from -1 to 2, I would notice that this point right here, this is going to be my absolute minimum. And this point right here is going to be my absolute maximum. For this next one, I'm graphing it on the domain also from -1 to 2, but not inclusive. So here I would have open dots. So same graph, but with open dots at the end. And then for this one, I actually only have an absolute minimum. I have no absolute maximum. With that open dot there, basically, if I were to zoom in on that point over and over and over again, it just gets really, really close to a y value of 4, but it never actually reaches a y value of 4, so no absolute max there. And then if I look at the function of x cubed plus 2 on the domain of -infinity to infinity, I can see that there is no absolute minimum, nor is there an absolute maximum. Okay. So note, suppose that we have the ordered pair C, f of C, and that is the absolute maximum point. Then we say that the function f has an extreme value at C. And f of C is the global maximum value. Let's look at some more definitions. If C is the number in the domain D of a function f, then f of C is called a local maximum if f of C is greater than or equal to all f of x values for x near C. And f of C is a local minimum of f if f of C is less than or equal to f of x for all x near C. And keep in mind that you may have heard of these concepts before, and just keep in mind that relative is the same as local. So here, if I have an absolute maximum, right, this would be a relative or local maximum. And then this would be a local or relative minimum, because there's no absolute minimums, because this function here goes down, down, down forever and amen. So there's a difference between an absolute extrema and a local or relative extrema. So let's take a look at this function here. Sine of x as x goes from -pi to pi over 2. It helps to look at a graph, so let's create a graph. And then let's identify our absolute and local maximum min points. So first of all, I can identify right here, I have an absolute max, and I also have a local max. And that's at this point, pi over 2 and 1. And then here, I have an absolute min and a local min at this point of -pi over 2, -1. And then this one here, I would consider this a local max. And that would be at the point negative pi and 0. So let's look at Fermat's theorem in critical numbers. If a function f has a local maximum or local minimum at c, at some value c, and if f prime of c exists, then f prime of c is equal to 0. So what we're talking about is critical numbers are where the derivatives are 0, or where there are horizontal tangents. So let's look at the converse of Fermat's theorem. Is it also true? If you have a critical number, does it mean that f has a local maximum or local minimum at c? Well, this is a big nope. Let's just look at the example of a graph of x cubed plus 2. We've got f prime of c is equal to 0 when c is equal to 0. So if we look right here at this point, we have a horizontal tangent, but this is not a max or a min. This is actually a leveling off point. So the converse of this theorem is definitely not true. What they're saying, though, is that as long as you've got a function that's defined at c, and if you have a critical number where the derivative at that critical number is 0, or if f prime of c does not exist at that point, then your c is called a critical number of f. And that critical number may or may not have a maximum or a minimum. All right, let's look at some examples. So what we're going to do right now is find the critical numbers of these following functions. But what we are not going to do is determine if they are for maximums, minimums, or leveling off points. We're just going to practice finding the critical numbers. So the way that you find the critical numbers is always as follows, okay? You basically find the formula for f prime of x, and then you solve f prime of c equals 0, where those x values are your critical numbers. So let's go ahead and do that. For these types of problems, because you're finding where they're equal to 0 or where they do not exist, for these types of problems, you do need to completely simplify your functions so that we can solve them. All right, here we're going to use the product rule. So here's my first and my second. So for product rule, I'm going to take my first function times the derivative of the second plus my second function times the derivative of the first. And then I'm going to clean that up a little bit. Now for this function, since I already have an LCD in place of e to the 3x, which is very exciting because it's less work for me. Of course, it's so exciting I can't even write a smiley face. I can easily simplify this. I'm going to end up with f prime of x is equal to 2x minus 3x squared all over e to the 3x. All right, so f prime of x found and completely simplified. Next, I'm going to find c's. Okay, so I'm going to find my c's. So I'm going to find where f prime of x equals 0, and I'm going to find where f prime of x does not exist. All right, so f prime of x currently, if I'm going to take this function here, and I'm going to set this equal to 0, This happens when my numerator is equal to 0. So that's what I'm going to solve. Don't use linear methods for solving. Remember, whenever we solve something that's not linear, we set it equal to 0 and then we factor some stuff out. So in this case, I'm going to factor out x, and then I end up with x is equal to 0, and 2 minus 3x is equal to 0, which if I subtract 2 from both sides and divide by -3, I'm going to end up with x equals 2/3. So here's one critical number. Here's my next critical number. If I want to see where f prime of x does not exist, that's when my denominator, in this case, because I only have an issue, a domain issue with this for the denominator, but the denominator is an exponential function. And an exponential function, if it's just like this and I don't have any plus or minuses in the base, this bad boy is never going to equal 0, so this is no solution. So I'm going to have x equals 0 and x equals 2/3. Okay, for this example, one of the first things I'm going to do is I'm going to rewrite f of x. I'm going to rewrite it so it's a little bit easier for me to do the derivative. Right now, the way it's set up is I would have to use product rule and power rule. And I'm going to do a little math smoke and mirrors first. So I'm going to rewrite x as the square root of x squared. And then that way I can bring the x squared inside. And then I'm going to rewrite the square root as the 1/2 power. And this guy, this could be a lot easier to take the derivative of. So let's do it. But we do have lots of simplifying at the end. Okay, so f prime of x, I'm just going to take this 1/2 and bring it down in front. I leave the inside alone. I reduce the power of 1/2 by 1. And now I multiply by the derivative of the inside. So this 2 is going to multiply the 4 and then reduce the power by 1. And then this 4 is going to come down here, and then I'm going to reduce the power by 1. So then let's simplify. This ends up being a fraction. In the numerator, I'm going to have 8x minus 4x cubed. And the denominator, I'm going to have 2. And the square root of 4x squared minus x to the 4th. Now notice, a couple things can happen. First of all, I can factor a 2x out of the numerator. And in the denominator, I can factor that x squared, that square root of x squared back out, which gives me this. And then notice that those two x's cancel each other. So I end up with f prime of x equals 4 minus 2x squared all over the square root of 4 minus x squared. All right. So once I have this, let's go ahead and find the critical numbers. So remember, step 1 is taking the derivative. Step 2 is you're finding those critical numbers, what you want to do is you want to set your derivative equal to 0 and find out where your derivative does not exist. So in this case, if I look over here, first if I'm going to find where my derivative is equal to 0, that actually happens just when the numerator is equal to 0. So, and that should make sense. Think about this here. If I go up top here, if I have a fraction a over b and that equals 0, that means that a is equal to 0. And we know that that's the case because we're not allowed to have zeros in the denominator, right? So if I have a fraction and I'm setting equal to 0, just set the numerator equal to 0. And this is not linear, so when I solve this, I'm going to subtract 2x from both sides, 2x squared from both sides. Then I'm going to divide by 2. And then I'm going to take the square root. And what I end up with is x equals positive or negative square root of 2. So here are 2 of my critical numbers. So again, first we look for where it's equal to 0. Next, we look for where it does not exist. So if I have this function, this fractional function, I need to look at, it's actually a fractional and a radical function. I need to look at where it doesn't exist. Well, there's 2 places where it doesn't exist. The first one is when this equals 0, when the denominator equals 0. So, and that happens when the numerator is equal to 0. Or sorry, not the numerator, the radicand is equal to 0. And if I solve this for x, I just add x squared to both sides and then take the square root, and I get x equals plus or minus 2. So here I found 2 more critical numbers. All right, and then actually there is like a little bit of a gap in here where I've got my 4 minus x squared, but it's outside of the domain, so I don't have to worry about the other values. Okay, in other words, I guess what I'm trying to say is that there's this radical, and remember that the inside of a radical needs to be greater than or equal to 0. And then the equal to 0 is covered there. The greater than, we don't have to worry because it's outside of the domain of the derivative. All right, I hope that made sense. Here we go. We have 1, 2, 3, 4 critical numbers for this example. Notice, all we did was find the critical numbers. We didn't identify if they're maximum or minimums yet. That's a coming. So let's look at the extreme value theorem. If f, a function, is continuous on a closed interval, ab, then f has both an absolute max and an absolute min in the interval ab. So in other words, here's a, here's b. Imagine I've got some function in there. I could find an absolute max in there, and I can also find an absolute min in there, and in this case my absolute min happens to be the exact same of that little endpoint. Another way to look at it, and again remember that this is a closed interval. And here I've got an absolute min, and here I've got an absolute max. If you're trying to find absolute extrema on a closed interval, we've got a couple of steps we want to follow. So if you're trying to find the absolute maximum and minimum values of a continuous function, it's extremely important that it's continuous, on a closed interval, AB, here are the 4 steps you're going to follow. So first of all, find all the critical numbers of the function f on the open interval a and b, or a through b. Next, you are going to evaluate the function at each critical number in the interval of a to b. Next, you find the values of the endpoints. So take a and b, plug them into your function, see what you get. And the absolute max value is going to be your largest output, and the absolute minimum value is going to be your smallest output. So just kind of notice what we're doing. Again, first of all, it's got to be continuous, and it's got to be a closed interval. First thing you do is you find your critical numbers. Okay? Next thing you do is you plug all your critical numbers in. Okay, so you find all the values of your critical numbers in your original function. Next, you check your endpoints. You look at f of a and f of b. And then last, you basically are comparing your answers. Okay, so you're going to compare, and who's the biggest, who's the smallest. All right, let's try an example. So here I need you to find the absolute minimum and maximum values of this function. So first things first, let's take the derivative. So a nice pretty derivative here, huh? No funky tricks, product rules. So f prime of x equals 3x squared minus 6x. Next, let's find our critical numbers. What we're going to do is we're going to set our f prime of x equal to 0. So 3x squared minus 6x equals 0. Let's factor a 3x out of both of these. And then I've got a critical number at x equals 0. And a critical number at x equals 2. All right, so I found my critical numbers. This is my step 1. Step 2. And actually, I'm going to write this as a step 2 and 3. Essentially, what I do is I am just going to do an input-output table. And I'm going to plug my critical numbers, 0 and 2. And then I'm going to take my closed interval numbers, -1/2 and 4. And I'm going to plug those into my original function. Okay, don't get it mixed. This is your original function. So when I plug in 0 into my original function, I get 1. So 1 cubed minus 3 times 1 squared plus 1 gives me 1. If I plug 2 into my original function, I get -3. If I plug -1/4 into my original function, I get this answer as a decimal here, and don't round your answers. So 0.796875, or I could write this as a fraction, 51/64. And then for the number 4, if I plug that in, I end up with 17. Okay, so my last step here is my compare. All right? Okay, so my absolute maximum, who's the biggest? That's right. My absolute maximum is 417. Okay, my absolute minimum, we look to see who's the smallest. And bingo, right here. And those are the answers. Oh, what an interesting spot for me to put a graph. Oh, but also keep in mind that you should be able to verify this with a graph here. If you look, here is your absolute maximum. Here is your absolute minimum.